Now on to our presenters. Today we have with us our senior engineering consultant, Alan Bellenhausen, as well as our lead engineer, James Molman. Alan?
Okay, thank you, Jack. First, I'd like to thank everybody for the interest that you showed in our white paper in the T&D World magazine, which is what got you the invitation to today's webinar. And then also thank you for registering and signing on for the webinar today. Today, we're going to talk about Transient Voltage 101, but we're going to be talking about a lot of things to get you to where you have an understanding of various power problems. And the way we're going to do that is we're going to be talking about a couple of things in particular, how they impact your operation, and also what you can do about it. And then to give you the understanding, we're going to be covering 4 topics. The electronic age challenge, and you'll understand that when we get to it. We'll be going over the various power problems, and then we'll dive into the subject matter of the transient voltages. And then at the end, we'll talk about solutions. So we'll start out with the electronic age and why good power quality is more important today than it ever has been. We're going to take a little trip down memory lane with some history. We'll talk about the technical benefits and then also the challenges that that technology brings. So the history. This is a hard slide to read, even if you've got it right in front of you, but the idea behind it is back in 1904 was the invention of the vacuum tube, and that was really the beginning of electronics as we know it today. And the takeaway from this is you can see the various steps that we took in electronic technology advancements. And it was 43 years between the time of the vacuum tube and when the first transistors were invented. And then it was another 24 years before they came the microprocessor age. And then it was another 5 years or so before we actually got into personal computers and the use of microprocessors in personal computers. And then you look at the duration between now and 1904, and you look how far we've come with supercomputers, you know, the Pentium dual core processors, the supercomputers. And the takeaway from this is that it took us there was a lot of time between early advances, but today the advances are coming at us at every turn. Every year there's more and more technical stuff, more technical components and in use and everything. James, you want to comment on that?
Yeah, thanks, Alan. So from my perspective, just as we think about this, the complexity of the world we live in today, you know, it wasn't too many years ago, you would go to a gas station and it was basically a mechanical assembly. You flip the lever, you squeeze the trigger, the pump turns on. It's just a simple pump motor, to where today everything has microprocessors embedded into it. And we have a digital world today to where everything is app-driven or becoming app-driven, to where there's personal and immediate feedback to things. So we see a world that is rapidly expanding with the use of electronics. They're getting smaller. One of the things that this timeline also highlights is the fact that the voltage levels have reduced drastically as well. So what used to be minor noise in the past can be significant noise enough to interrupt processes. So there's just a lot of things that we need to think about in the world going on around us today. You know, we just see electronics and microprocessor controls into all kinds of things where we never used to think about them today, and that's part of the caution we need to bring up.
Thanks, James. So as James was saying, electronics are being integrated into more and more electrical equipment. The pictures in this slide just depicts several of the things that used to be more of an electromechanical type situation, but now they're using electronics to control air conditioners, refrigeration, elevators, all these things that you see. Even the simple LED lights have integrated circuits in them, and they're more and more sensitive and causing more and more challenges for us.
Alan, there's another quick point here to bring up. In the efficiency world and the idea of improving things, of trying to get better constantly, of making things more efficient. Not only do we see electronics, but we see variable speed, variable control, all those things. What used to be a simple motor starter has turned into a variable speed drive of some kind, a frequency drive. So again, the complication is twofold. Not only is things getting more complicated, but some of these technologies are also highly corruptive. Meaning that the noise, the harmonics that get put up from frequency drives and those type of, ballast systems, switching mode power supplies, all these things are putting a lot of contamination into our electrical systems. We need to understand that in terms of what protection we should be using and what's the tolerance and immunity of our equipment.
So that's a good lead into our next topic, which is talks about the technology benefits and all the improved performance, the way our lives have been made simpler and controlled by all these electronic devices. We have several things that we benefit from, like the remote monitoring and control. That brings to mind, I have a utility background, so I think about the SCADA systems that we had. We were able to monitor equipment, monitor the condition of it, the indication of what the status was. So that's all a lot of the new technology, but it even has advanced since my time in the utility, and now you can get cellular notifications if something's going on. It just doesn't go to the SCADA. Now it sends out alarms to maybe the people that you want to respond to those alarms. We've got a lot better production control. We have all these systems that have programmable logic controllers with inputs and outputs, and they're tied to servers that are monitoring all kinds of pieces of equipment or processes or robotics, and it's made it an automated system versus all that stuff being manual. You have to manually control it or even manually monitor it. Believe it or not, lower utility costs are a benefit of this technology. You just think about, James mentioned the high efficiency HVAC systems with the DC variable motors and compressors, and then I mentioned about LED lights, that all those things consume a lot less electricity than before. So it's also lowering the consumption, which lowers the utility cost. The robotic controls, look at the impact of manufacturing. I have a CNC machine, and I know today it's very easy to put in a design and it creates all the nodes and writes all the code. But in the early days of the CNC machine, you had to be able to write code and write all those. Every time that CNC made a movement, you had to write a code for it. Now it happens with a push of a couple of commands and it creates itself. So those kind of things they're allowing us to do a lot more with a lot less in every respect. How did we ever do it without this advanced technology? So along with all those benefits also comes the challenges that we were talking about. These very small, intricate, integrated circuits are vulnerable to a long-term degradation of the system. They have damage going on with them all the time just from being hooked up to electricity, really, and effects of load switching and that kind of thing. So it's an everyday degradation of the small components. You also have catastrophic facility damage. And we think about those in the big surges, like the lightning surges and the utility grid surges that cause immediate damage to equipment. Maybe it doesn't fail it, but it can cause the immediate damage to it. And then the equipment downtime. In a manufacturing process, there's all kinds of things that happen that they think they're chasing ghosts all the time because something happened that didn't make it right, and now you don't know what it was, you don't know what it caused it, but it's working okay. But it also caused a downtime, a loss of production.
You know, Alan, along with that, you know, the idea of what goes on in the PUC today. You know, any event that causes a loss in output, a loss of, you know, serviceability to the customer, you now have to report that event. You have to troubleshoot that event. And so what used to be pretty insignificant in the past becomes a lot of work today, especially, you know, for instance, in the utility world and what we do to our customer base. There's a lot of things that are not necessarily earth stopping, but one little glitch, and all of a sudden you've got to deal with a whole bunch of issues.
Yeah, that also brings to mind the legal issues that manufacturers have. That if something goes wrong, if you lose Wi-Fi or you lose the cellular signal and somebody needs an ambulance, you never know where you're going to all of a sudden become liable because your equipment wasn't reliable. Then there's the process disruptions we've been talking about. The power quality problems can cause little disruptions to processes that are going on all the time. I've got a good example of that. We have a client in the oil field, and they're in a manufacturing plant, and what they're manufacturing is drill stem for the oil field. And what they provide is they make the drill stem, cut it into the lengths that they need to, but then they put a whole rack of this pipe onto a machine that pulls one joint of pipe off a pipe at a time. It threads one end, and then it moves the pipe to the other end, and it threads both ends. So both ends are threaded. They come back in. It runs 24/7. They just keep the pipe rack loaded up. Well, one morning they came in, and they had a whole pile of 40-foot long all thread. It didn't stop threading, and as it moved the pipe, it kept threading. It threaded it from one end to the other. And of course, they were pretty upset because there's not much market for 40-foot long all thread. So it was just a process disruption that happened to them. And of course, they're just a flat out equipment failure. I skipped the data loss and corruption. That's a big one for like data centers and those kind of folks. And just a small glitch in the electrical system they can either lose data or they'll get a bunch of corrupted data that they can't do anything with. So, and then we get to the equipment failure that we talked about. But all these failures and all these challenges all increase operating expenses. And so, an interesting fact is that according to the Lawrence Berkeley National Laboratory, power-related problems cost companies over $80 billion a year. And so this number is just going to continue to grow as electronics are integrated into more and more electrical equipment. So now we're going to move into the power problems. And I can tell you, I mentioned that I'm had a utility background, and a lot of these power problems were very well known to the electric utility industry, such as the overvoltages, undervoltages. Harmonics was a big one that we always on, power factor. But from just a manufacturing or layperson's standpoint, they're important to them. But one thing that we never even talked about in the utility business was transient voltages. So we're going to start out with just a touch about transient voltage, and we'll get deeper into that later on. But transient voltages or surges are inherent to every electrical system, and they're extremely fast. And this says 1/1,000,000th of a second, but they can be extremely fast. And it's hard to imagine 1/1,000,000th of a second. But they're there. They happen multiple times a day, and they're just a result of electrical activity. Every time a load switches off and switches back on, it puts these little transient spikes into the system. And those are the small ones that probably don't do catastrophic damage, but you're still having the latent damage. And it's not new. They've always existed, but that's why we walked you through the history of electronics to say they weren't damaging the old hardened electromechanical type things. But now that we have the integrated circuits, everything's digitized. It's catastrophic to those things in the smallest way. And then here's the idea that transient voltages are created inside of your building, and it's to the tune of 60 to 80%. We all associate transients with that lightning strike, that lightning surge, or if something happens with the utility on the grid and you have a dip in the electricity or a brownout, or they're just switching power factor correction on their system. Those kind of things, we see those kind of glitches. We see the lights blink. We know that there's things happen. But what we don't see is all those transients that are created right inside your own facility. And we'll get into that a lot further. So the effects of transient voltage surges are that we have the short and the long-term electrical equipment damage and process interruption and misoperations. So those that happen from the inside of the building are normally the more long-term electrical, and then the short-term immediate are that other 20 to 40% that we normally associate with lightning and those kind of things.
Alan, again, in the modern world we live in today, with all the changes we deal with, these minor interruptions can be as bad or worse than actual damage. When you think about it, if something stops and you just have to go restart it, it's not that the equipment failed, but the process of having to deal with the interruption can be just as bad as failure. If you're in the middle of a process that's time critical or temperature sensitive, and you get one glitch in the middle of that, it means you have to throw away all that product and start over. So again, there's a side of this whole transient protection side that gets overlooked sometimes, and that's just understanding that a lot of these misoperation system glitches, whatever term you want to use them as, they can be fixed. They don't have to be there. Good design, protective measures, they do a lot, especially with the complexity of our systems today.
Yeah. Those kind of inconveniences that you're talking about are generally the more expensive type things, where you've lost production, they cost you money, not necessarily in equipment, but in production or time. So let's move on to the next power problem, which is a common one. It's overvoltage. And we've all seen this at some time, generally not for a long period of time, but just a temporary overvoltage causes problems. And it's defined as a rise in voltage that's greater than 5% increase in voltage. So as an example, in the United States on a 120 volt system, which is the most common, if you have 126 volts or more, that's considered an overvoltage. And the effects of that are that it will damage the electronic component. It will actually cause failure in some of these. Just the overvoltage violates the dielectric strength of these small components. Yeah. And the cause of this is generally, there's several things. It can be a misoperation of utility equipment, the voltage regulators that are providing you the constant voltage. But it can also be a huge drop off of load for the utility. Whenever that large load drops off, the voltage automatically spikes and it's too soon, too fast for the regulation to catch up to it. It takes a few seconds for that regulation to actually change taps in a tap changer and get the voltage right. So it's not something that the utilities can exactly instantaneously control.
And to that point, Alan, I think this is a good topic here to think about for a second. Now that we're headed into the summertime, at least in our part of the world, the demands, the utility, or the heat, the cooling demand, I guess I should say, dealing with the heat problems, the demand on our electrical system can be pretty high in the summer. So what does the utility do to compensate for that demand? Instead of a system that's set at 120 volts as far as usable voltage, they set their system to run at 126 volts because they know there's going to be a dip in the system. Well, now you're going to get that rebound effect that every day, certain times of the day, in the evenings in particular, all of a sudden your load demand goes down. So that 126 volt voltage threshold is going to now be exceeded. And so you're regularly going to run out of tolerance.
Right. So the opposite of that, and which also can happen from the huge loading, is whenever you get huge loads, you can go into an undervoltage event. And an undervoltage is defined as greater than 10% loss in voltage. So if you get down to 108 volts, it's gonna be a low voltage, undervoltage. And this is where you get process interruption and actual overheating, because when the voltage goes down, the current's going to go up. So it's still consuming the same amount of power. So it's just a physics thing that current's gonna go up and cause some overheating and it'll cause damage. The next one that I'm going to cover is harmonics, and this is one that utilities focused in a lot back in the 70s and 80s, and it was all about the types of load that utilities were having to serve, generally caused by large arc furnaces or even the onset of static bar compensators would cause these harmonics. But the most common are the inverters, DC converters, and the variable frequency drives. But these harmonics that they create is just a distortion to the fundamental sine wave as depicted in the slide. And it can be both voltage or current distortions, and it can be minor or it could be very, very severe. And the effects of it are overheating components and equipment. The next one's something that's been around for a long time, the noise, or the EMI or RFI, noise radio frequency interference. And it's just distortions on the sine wave. And the effects of this is where you get the corruption of your data or actual signal loss. The last one we're going to talk about is the power factor imbalance. And this is caused by inductive loads, and it can happen on the utility side, but it can also happen in your facility. And utilities pay particular attention to this, because if you drop below 90%, you're going to start getting a penalty or an adjustment to your bill, because the utility actually has to increase the amount of power it delivers to you, because it's got to overcome that 10% loss in power factor. So that's something that you want to watch. Typically, individuals, we don't have to worry about it at all. But anything that where you have a large loads coming on and you're paying a demand charge, you're also going to be subject to the power factor imbalances. So James is going to wrap up this section on the power problem effects.
Yeah. So Alan, as we've discussed these ideas, I mean, these problems are normal. They're somewhat day-to-day events. They all happen. There is a point that we wanted to bring up here to illustrate, is that each one of these power quality challenges, power factor, harmonics, noise, overvoltage, undervoltage conditions, every one of those events is a shock to the system, or some kind of not a damaging event necessarily, but anyway, it's a shock to the system. So at a minimum, whenever you have one of these factors take place, there is a transient associated with these power quality events. Meaning that, when these things happen, it's not just the undervoltage events you have to contend with. You have to make sure your system can handle the associated transients that are coming through with these power quality conditions. And that's one of the challenges that, again, kind of gets overlooked from the transient world, is that there is an effect here that can be mitigated if you design your system around it. But you have to incorporate that, and you have to remember that even an undervoltage or a low power condition, something caused that system to change. There was a shock in the system, so there are other things besides just the low power condition going on, or the low voltage condition going on.
Yeah, and I guess the takeaway I get from this is that there's things that can be done for power factor, for harmonics, noise, all those things. But even if you're taking care of those, you're still going to, if the event occurs and you take care of it with some kind of filtering or whatever, that transient happens, and none of the things that the correct power factor or correct harmonics or correct noise or over voltage or under voltage take care of or mitigate transient voltages.
Yeah, good point.
So the next thing we're going to do is we're going to step into a little bit more science about the subject matter, which is transient voltage. And we'll start out with talking about the stability of our systems. We've got an IBM study we're going to kind of summarize for you. And then the transient sources, where the heck do they come from? And then what are they actually doing to your equipment, your systems? So transient, let's talk about voltage stability versus transients. We know what we want. We expect that the voltage is stable, that it's consistent, it's reliable, and it's predictable. But we also know that what we really get is, because of the transients, is unpredictable, they're unexpected, and they're really hard to identify as a problem. They're hard to capture. They're hard to, it's not something you see. They don't blink the light generally whenever you have a transient. It's that ghost thing I was talking about. People were chasing and didn't know where the heck what happened or why. So this was the IBM study that we were talking about, and what this is IBM knew that they were having a multitude of power problems. They just didn't understand what was causing them, what they were. So they sanctioned a study on IBM equipment at 200 locations in 25 cities across the United States. And it took a 2-year time span to complete this study. And what they concluded from the study was that 88.5% of all the AC power problems are transient related. And that the majority originate from inside the facility. Remember that 60 to 80% that we talked about, only the 20% comes from the utility or outside. And in their study, they said that sags and swells are responsible for only about 11%. And then that little 0.5% that's left over was just power outages. And that's something that if it goes out, it goes out until it comes back on. But why is this significant? It's just the sheer scope of the study. Imagine 200 locations in 25 cities and taking over 2 years. IBM paid a lot of money to get these results. And the thing about it was done by a major corporation that has no affiliation with surge protection companies at all. They just wanted to know what was causing the problem. You can't address the problem if you don't know what's causing it. And they took an engineering approach to figure it out.
And I like that study, Alan, because it highlights and draws attention to one of the things that kind of gets overlooked to a certain extent. We've talked about microprocessors being embedded in everything. Well, you now have basically this computer control inside a lot of small electronic control systems. And so the use of these computer type systems has, again, expanded rapidly. Everything from utility systems where they're monitoring and collecting data, doing SCADA systems, to the manufacturing world where it's all process controls, and there are so many different control systems and controllers dedicated to exact sciences, trying to make sure that we control things within a very tight tolerance, a very tight range. Because we're getting better, we're getting more efficient, we're trying to reduce our scrap, we're trying to reduce our costs. These are all great things, but the protection needed as far as understanding what it takes to keep those systems operating correctly has increased as well. And this is kind of one of those hidden areas where this part of it of equipment protection hasn't kept pace with all the technology increases.
Exactly. So I told you we were going to talk about where do these transients come from? And you've heard this several times already during the presentation, but everybody thinks of transients as the lightning or the electrical accidents, a vehicle runs over a pole, or capacitor switching, or those kind of things. But it's only 20%, plus or minus some. But whenever you look at all the other sources that are out there, they're variable frequency drives, any power tools, air compressors that come on, copy machines. People don't realize that little heating element in there to dry the ink on the paper. Every time it comes on, it's a transient. And imagine running through a copy machine, 100 copies, and it's every time that thing turns on and turns off. Again, we talked about air compressors. Air conditioners are self-destruction machines with a compressor and a fan, condensing fan on it every time it starts and stops. So it just goes on and on about all the things that cause transients. And one thing to note, the internal, the 80%, they're more frequent, and then they cause more of a cumulative damage, or we refer to it as latent damage, and we'll talk about that a little bit later. But also, the external are those less frequent, but they're the big ones everybody thinks about. After the storm and they've lost a TV set or an appliance or something, they know they've had some kind of lightning event that caused them to have an immediate damage to their, and we call that catastrophic damage, is what we refer to that as. So here's a little illustration about these latent and catastrophic events and the types of failures. And I'm going to use the mouse to move around. And I'm sorry if there's a delay because of we've got people all over the place logged in. But latent is, think of latent as all these small little spikes. We've illustrated with lightning surges, but they're small. And they're just, with every one of these, there's some degree of degradation or process interruption or misoperation, those kind of things with every single one of these. But we have the big catastrophic, and it just takes the one big one, and it causes immediate damage. But the takeaway from this is that last latent one, the last straw that breaks the camel's back, has the same consequence, the same failure modes as that one big one. And I like to refer to this as death by 1,000 cuts. 1, 2, 3, 4, 5 cuts might hurt you, but you get to that 1,000th one, and you're going to have the same catastrophic consequences as somebody pushed a sword through your heart. Yeah. So that's the two types of, and the explanation. It's a good graphic. So now let's talk about the solution. How do we mitigate the impact of these transients? They're going to happen. You can't keep them from happening. So what do we do to actually mitigate the effects? So to help you understand this, we're going to talk about a concept that's the immunity level of equipment. And this is what the level of voltage that a piece of equipment can take for a period of time, and it shouldn't affect it. So we say immunity level of 2 to 1 or 3 to 1. Whenever we say 2 to 1, that's the rule of thumb for sensitive electronic components. The 3 to 1 is more like for motors, that kind of thing. That's why we list 2 different ones. So not every piece of equipment has the same immunity level, but we want to explain that 2 to 1 and 3 to 1. Now, what we have here is a sine wave, and we're going to say for illustrative purposes, this is a 120 volt sine wave, and it's in this green area. And this green area is the 2 to 1, 3 to 1 immunity level. So from 240 volts to 360 volts, that's the immunity level of the equipment. If you go above that, it starts getting in yellow and then red, pink, and then actually red. And that's going to be, if you get way up there, that's going to be the really damaging effects.
And so, I'm sorry to interrupt. I have a question here. 2 to 1, 3 to 1 of what?
Good question. The nominal voltage. So if the nominal voltage is 120 volts, then you can take 2 times 120, and it'll be 240 is the community level.
Yeah, that's good.
Okay.
Again, it's just, and that voltage can be AC or DC. So whatever your system voltage rating is, let's say it's a 24 volt control system, anything that exceeds twice the rating of 24 volts, 48 volts, the system is tolerant up to 48 volts. As soon as I start breaking above 48 volts for DC, that's when I start seeing component failures and overheating and degradation.
Okay. So now we have an illustration of the latent failure, the smaller transients, the ones that happen more frequently, and they have the same cumulative effect as we talked about earlier, and that's the same effect as a catastrophic transient failure, damage or degradation or misoperation, but it takes a lot of them. And you can see they're in this yellow and orange range, just above the immunity line. So then we have the depiction of that catastrophic failure, which is a single transient event that causes that immediate equipment damage or failure. So we want to talk a little bit about types of transient surge protection devices. And we show plug strips, built-in components, commodities, and what we mean by that is just something you get on the web, go on the internet, you buy it on Amazon, it comes to you, and you don't get any help with the application, you just put it on. But what people don't realize is, and what's important is that how you figure out what if a surge protector is doing any good is if it clamps, the clamping voltage is beneath this immunity level. Most of these commodity components, plug strips, clamp at greater than 900 volts. So you can see that's more like 6 or 8 times the nominal voltage, and they're not going to. It'll protect you on maybe some of the great big strikes, and it'll only protect you 900 volts, but it still doesn't get you down below that immunity level.
Yeah, so I guess, Alan, the point for me with all this is, be careful what you get. SPDX versus SPDY are different. They have different performance, different characteristics. Spend a little bit of time investigating what you're getting so you understand what kind of protection you're really going to get. And those minor things as far as, okay, an SPD is an SPD, well, that's not quite true. It's like anything else. You have high quality components versus generic components, and you need to understand what you're doing and make sure you look at the total immunity level of your system and your components and the objective of what is it I'm trying to meet, what's my goal here. In other words, do I want a safe, reliable system, or do I just want to stop equipment from catching on fire? You have to understand the evaluation process and look at it from your terms as far as what's important to you.
So you'll notice that there's a new line on this diagram, and it's slightly below the immunity level, and this is where a maxi volt clamps at 180 volts on a 120 volt system. So you can see if maxi volt's going to clamp at that level, it's going to keep the voltage from going any higher than that 180 volts. So it clamps, chops off, whatever you want to call it. In the industry, we call it clamping, but it's going to clamp it at that 180 volts, which is well below the immunity level of the equipment at 120 volts.
So just another quick clarification here. One of the things that's interesting about this whole idea of voltage protection is this industry doesn't use the term voltage protection very well. In other words, when you buy an SPD, a surge protection device, most of the time you see this parameter that talks about surge current rating. Well, to the equipment, is it the current that's the problem, or is it the voltage that's the problem?
If it's the current that's the problem, you have overcurrent protection built into your system because you have circuit breakers.
Right. And so again, that's kind of the thing we're trying to illustrate and point out is you need to understand the voltage limitations, the voltage requirements. Our industry kind of doesn't really focus in on voltage protection as well as it should, but that's one of those things that where, when we look at things from an equipment perspective, when we look at things from a reliability perspective, the surge current is more for lightning protection, which a lot of times relates to utility lightning arresters out on the pole for power distribution. Most of the time, lightning currents get on high voltage transmission lines or distribution lines. They're not really down into the equipment level. But the voltage application, the voltage level, it has a lot of fluctuations, a lot of transients go through into the low voltage equipment, even though upstream we think we have lightning protection on there, and we kind of miss the actual reliability component of what we're doing to make sure that the voltage limitation works effectively and well for the equipment you're trying to protect.
Yeah, I guess all of us have experienced some kind of equipment damage at our homes. We lost a TV or something after a storm, and I work for the utility company, so I know how it goes. People call the utility company and say, "Hey, I had a storm come through and I lost my refrigerator," and they'd say, "Well, we're sorry, we're not required to protect your equipment. We're just required to protect our equipment and understand their equipment's high voltage, high VIL. It's meant to be able to withstand high impulses. It's built that way for a reason, and if they're just protecting above that high impulse capability, you're not getting any protection in your home. And it's sorry, if you need that protection, you need to seek it out. You need to provide it yourself." And I've told that to a lot of people, and I've heard it myself. So let's move on to the next area where we're an application example. So now that you understand the immunity level, let's talk about that application. And picking a surge protection device is very easy if you know the nominal voltage level and then what the immunity level is of that equipment you're trying to protect. So you look for a surge protector that has that clamping voltage within that immunity level. But the very technical, very specialized side of surge protection is knowing how and where to apply those people. And it is very technical, and you need technical assistance with that. And that's one thing that we provide as a company. We can help you with that application and walk you through how it needs to be applied, where to. And this is an illustration of some of the things that you have to consider when you're applying voltage protection, transient voltage protection. The illustration shows a power pole with a transformer on it taking a lightning strike. And for 40 years when I was in the utility, I always thought that if you had a lightning surge on the utility and it went through the transformer, what does the transformer do? It transforms high voltage down to a lower user voltage. Well, in my whole career, I assumed that transient spike was being transformed as well. It was being reduced to a lower level, but that's not the case at all. Transients are very high frequency, and this is really technical, but high frequency voltages pass right through a transformer. It's like it passes it because the capacitive reactance of the transformer at the high frequency. And so that surge is going to go right through that, from that utility line through that transformer and then into your system. And in this illustration, we have a service entrance panel. And there's the lightning arrestor on the pole. But then at the service entrance panel, you need protection at the right voltage level. Typically, like in a manufacturing or industrial or commercial facility, the first panel is 483 phase. And so you need a surge protection device that has the immunity level for 480, which is someplace around 11 to 1200 volts. Well, our protection clamps at 940 volts. So you can see it clamps at a good voltage to protect 480 equipment. But then if you go to the next distribution panel where you've stepped it down to 120, 208, 3-phase, or just 120, 240 split phase, that 940 volts that is clamped on the 480 is going to pass right through your transformation to 120, but it's still that 940 volts is way above your immunity level. So you need to protect at that level, at the 120, 240, you need protection there. And then you'll have branch panels that come from your distribution panel, and they're a significant distance away. And remember what we said, 80% of the transients happen within your own facility at the end, at the point of use, not back up here at the utility. So if you have all your protections just here, then you're not protecting any of this equipment or the equipment that's attached to the same panel from transients that are created in your own facility. So you need to be the next step is you need to go down to the load, the point of service, the load.
Right.
Have equipment, true equipment protection. That's going to protect the equipment. It'll mitigate the transients and keep them from getting back into your branch and back into your distribution. Is that the point? James is putting his hand out saying, whoa.
So yeah, I just wanted to capture that thought and give it a chance to sink in a little bit, because there's a lot of practices out here in the engineering community that says, okay, I've got lightning arresters out on the pole, my downstream system is protected, that there's nothing going to happen from this point downstream. And that's really not quite accurate or appropriate. The other challenge to this concept of this cascaded or layered or stepped approach, that, you know, if I have 480, if I have a two-way distribution, if I have 120, and do I have control systems? You know, how do I understand the immunity, the reliability concerns? You know, there is no simple answer. You know, in the engineering community, we love to take a formula and say, here's the formula, apply the formula, here's the answer.
Here's the catalog number.
Yeah, just do this, you know. And it'd be great if it worked that way, but, you know, here's the trick to voltage protection is you've got to understand your system. You've got to look at the intricacies as far as what reliability am I trying to achieve. You know, am I a data center where I've got to have ultimate reliability? You know, am I a water wastewater facility where I can get fines and punishments because, you know, if a system shuts down and I get a spillover and I get contamination going in downstream, you know, that minor glitch turned into some $1 million fine.
EPA fine.
Yeah, you know, those type of things. You know, and so Alan, I just wanted to reiterate that point and just to think about that for just a second here, to understand that, look, there is no simple rule here of, you know, look, every panel gets a surge protector. That doesn't have to be done. To the point of, you know, in this simple illustration we have here, I got a 40 volt panel to a distribution panel to a branch panel to a load. That configuration changes a lot, where it may go from 480 directly to 120. I can go 480 down to 24 volts directly. So there's a lot of things that need to be thought about, and that's the process of trying to digest all this. And so I just kind of wanted to capture that thought real quick.
Yeah, thanks, James. And then there's the protection you put for equipment protection or the control voltage protection. So now I want to talk a little bit about MaxiVolt. We haven't really been having a MaxiVolt conversation until we got to explaining immunity levels and those kind of things. But we have value-added services that you don't get from other surge protection companies. And we provide specialized technology. Of course, it's the value-added services. We custom tailor. We are a manufacturing. We want to know what your problem is, what your issues are, and then we come up with an engineered solution for your system. And we try to extend the life and protect all your operational integrity and your electronic and electrical equipment. We also can assist clients with design strategies for grounding and wiring practices, and also system configuration. So we're not just a surge protection company. We are a solution company. We provide solutions for your problems. Now, I do want to encourage people to, if you have questions, to go ahead and get those questions in. We're drawing near to the end of the webinar. But if you saw something in this presentation in the webinar that either struck you as, aha, that's what my problem's been, or maybe it makes you question, maybe that's what my problem is. Or maybe you're the type of person that wants to be proactive and you don't want to have to deal with all those issues. If you need to give us a call, and we can help you with the right solution for your issues or the right proactive approach for your facilities.
Yeah, and so Alan, to your point, again, to actually do power quality correctly, It's not about sticking Band-Aids or some little widget out to take care of all my problems. There is no magic solution or no magic answer that takes care of everything. It's a matter of priorities and understanding what needs to get done first. But you have to look at the whole system. We can't just say, okay, I have a 40-volt system, therefore take this approach and it works all the time. The type of 40-volt system, whether it's a YY system, a delta power system, a corner grounded delta, all these other variabilities start throwing a lot of complexities and a lot of other concerns into there. And one of the things you mentioned here was good, was this whole concept of grounding. The NEC, the National Electrical Code, there are more changes to grounding every 3 years than any part of the code, because there's so much to it that it's one of those things that's not well understood. So those type of things need to be tried to digested. They need to be investigated. Investigated thoroughly. And again, all factors need to be considered as far as what you're trying to achieve.
And that does get very complex when you start digging into grounding systems. So, we talked about how we're a solution company. We go to our clients and find out what's happening and then provide solutions. And I'm not going to read these to you, but these are 3 examples of where we helped out industrial customers, oil production, water production, manufacturing, and all in these cases, and generally in all cases, they all realize a investment payback way before a year. In other words, they get their money back. They invest $29,000, $71,000, and within a few months, they've recouped that money. But then it goes on savings per year. The oil production I want to talk about, they spent a mere $20,000, and their annual payback year after year going forward is almost $1 million. And it makes perfect sense to make that investment, because good surge protection that really works doesn't cost you anything. It's an investment, and it's going to be making you money year after year after year, because you're not going to have the failures, the misoperations, and the system degradation. So in conclusion, Jack, why don't you wrap up the conclusion?
Sure. What I think, to summarize everything that I heard today, the amount of technology, the integrated circuit that is surrounding us in every operation impacts us all. And we are starting to see more and more people wake up to the challenges and try to find answers. And I assume that's why a lot of y'all are on today. And we know that the step 1 of the process, of course, is be aware you have a challenge. Step 2 is select a transient voltage surge suppressor that can turn on within the immunity level of the equipment. Then the challenge really begins, which is application. And so I thank y'all guys for really giving us the 101. It was a good, we stay in the shallow end, obviously, today on a lot of things. And we do have some questions that the folks like to address offline. So for y'all folks, we will definitely be reaching, or our presenters will be reaching out to you. For others, feel free, as Alan said, reach out to us. And I thank everybody for joining us. And I thank both our presenters, Alan, James, thank you for your time.
Yeah.